All right, we're ready to go. So let's find the speed of a geosynchronous. Remember, a geosynchronous satellite has a period of 24 hours. Okay? Spy satellites, which are much lower, travel much, much faster. Okay? And we'll look later on, I think when we get to the energy stuff in chapter 7, we'll look at the escape velocity from the Earth, how fast you have to be going to get out into space. And that has something to do with the energy level that you need. Okay, you've got to overcome the kinetic energy has to equal a zero potential due to gravity. So we'll look at all that later. But anyway, so let's just start with what is the speed of a geosynchronous satellite. First of all, we know the period, and then we can we're probably going to have to calculate the height first. Okay, we're going to have to calculate the height because here's why. Well, first of all, let's just look at this thing first. Okay, here we go. Okay, so determine the speed of the Hubble telescope orbiting at a height of 598 kilometers. Okay, so Hubble is orbiting at a height of, and they have to keep track of where it is. So it's going 7.56 times 10 to the third meters per second, almost 7,500 meters per second. All right, in its velocity orbit, and that's the square root of this of g times the mass of the Earth times divided by these two quantities added together, the radius of the Earth plus its height. Okay, so now we've got to figure out what the radius is of a satellite that is in geosynchronous orbit. All right, so we know this. We know that V is equal to GMR over 2 pi r times t. Okay, so we're going to use, we know the period. We know the period. So we're going to put these two guys together to figure out what V is, its speed, and also what R is. Okay, I think we're probably going to have to find R first because that's the easiest way to go. So we're going to find T first, plug that in, and figure out what R is. But you're going, wait a minute, you've got an R here, and I don't know the height, but I do know the period. So I've got one unknown, know the period, I've got one unknown. We just have to solve this guy. Okay, so let's do it all algebraically and then plug in the numbers. Okay, otherwise it gets really ugly. So I know this. I know that V, the speed of that geosynchronous satellite, is equal to 2 pi r over t, where I know t is equal to the period. T is equal to 24 hours. So far, so good. We're going to have to convert that all to seconds. But I also know that V is equal to the square root of GME over R. Aha! So I'll set those two equal together. Yay! Now I've got one unknown and one equation. So let's square both sides. That'll just make it easier. GME over R is equal to 4 pi squared R squared over T squared. So far, so good, right? Okay, so now let's multiply R by both sides. GME, multiply R here, multiply R there, is equal to 4 pi squared R cubed over T squared. Okay, so now we'll take GME times T squared, going to multiply both sides by T squared. See, the reason I did that is so I can get rid of that, but that became R cubed, see? So now I'm going to multiply both sides by T squared, so I get rid of that, is equal to 4 pi squared R cubed. And now I'm going to divide both sides by 4 pi squared. I get GME T squared over 4 pi squared. All right, so now is equal to R cubed. Okay, it's equal to R cubed. Now, what are we going to do? We're going to do this. you take cubed root of both sides. But what I'm going to do first is rewrite it as GME t squared. It's the same thing, divided by 4 pi squared, and put that into my calculator so that I can get what r cubed is. Then I'm going to take the cubed root of it. Now you have to be very careful with this calculation right here. First of all, t is equal to 24 hours. I got to get that into seconds, which is times 60 minutes per 1 hour times 1 minute, 60 seconds is 1 minute. So it's 24 times 60, 3,600. That is equal to 8.64 times 10 to the fourth, 86,400 seconds. Okay, that's what t is equal to when we're all. So we'll put that in, and I know that the mass of the Earth is 5.98 times 10 to the 24 kilograms. I know that g is 6.637 times 10 to the negative 11 newtons meters squared per kilogram squared. Okay, and I know 4 pi r squared. All right, so you got to be very. So I wanted to make sure that I showed you how we calculate this on the calculator so that you don't make a mistake. So double parentheses 6.637 second e to the negative 11 times mass of the Earth 5.98 second e to the 24th, close the parentheses, times t, oh, don't need to close, I got to get my t squared, parentheses, going this way, t squared, so I'm going to put that in parentheses because t is big, 8.64 second e to the fourth squared, close parentheses. Now I've got my numerator. Boom. I go ahead and hit that. It's a big number. It's a big number. And I'm going to divide. Now watch what I do here. I'm going to divide that answer, parentheses, divided by 4 second pi squared. You've got to make sure you put the 4 pi squared inside the parentheses. Because if you just divide by 4 pi squared, what will happen without the, you'll get the answer divided by 4 times pi squared. It'll screw it all up. So I wind up with this. I wind up with 7.5. Now this looks crazy. Basically what I've wound up with is 7.504 times 10 to the 22nd meters cubed is equal to r cubed. If I put all the units in here, if I put in the kilograms here, and notice the kilograms squared there cancels, put in the period there, divided by 4 pi, and put in the g here, I'm going to get, and I get the kilograms, so everything's going to go away. I get that number, and now I've got what r is equal to. I'm going to take the cubed root of this. So I'll go second answer. Now I'm going to take the cubed root. Math. Oh wait, I got to do this first. I got to go second math. I never use the cubed root. Gosh dang it! I never use the cubed root function. So cubed root of second answer. That's correct. 4.218. Now that's not how high the satellite is. That's how high the radius is, including the Earth's radius. So we've got an RE here, plus we've got the satellite out here. Okay, H. So we've got R is equal to RE plus H, remember. So we've got to subtract R minus RE is equal to the height that it went. But first we wanted to find out what its speed was. And so we've got the R that we need to find the speed, which the velocity then of this is 2 pi times 4.21 times 10 to the 7th meters divided by the period, which is the time that it takes to go around is a day. That's 8.64 times 10 to the 4th seconds. Aha, got meters per second. So look what I'm doing. I'm taking the R that I got times 2 pi divided by parentheses 8.64 second e to the 4th. There it goes. So those dish satellites and stuff are up there buzzing around at about 3,000 meters per second. Converted to miles per hour, it's about ballpark 7,000 miles per hour. That's how fast those stationary satellites are flying around the Earth. Spy satellites are even faster. Escape velocity, I think, is around 17,000 meters per second. 17,000 miles per hour, I mean. Cool beans. I love it. All right, so now, we needed to find the height. So we're also going to find the height of the orbit, and then that'll be it, and we will be done with this. And then I think you'll be armed and dangerous to do anything in class, and we'll look at some of the problems. All right. So R, what do we get for R there? 4.21. R is equal to 4.21. Now these are crazy calculations, aren't they? 4.218, or you could do 4.22 times 10 to the 7th raised to the Earth 6.38. Let's go with what their book says, times 10 to the 6th meters. So the altitude is 4.218 times 10 to the 7th meters minus 6.38 times 10 to the 6th meters. This doesn't look like it's going to be right. Let's try it. Oh, I knew I should have probably stopped it. Oh yeah, we're still good. I forget that this is 10 to the 7th, this is 10 to the 6th. I should have lost it. In other words, this is 10 million, and this is like in the millions. So it's huge. It's sufficiently huge. 3.58 times 10 to the 7th meters. Divided by 1609, which is how many meters are in a mile. It's about, 22,000 miles up in the air. 22,240 miles in the air. That's how high up they are. Jet airplanes fly at 5 or 6 miles above the air. Okay. So they're up there. All right, that's fun stuff. I like this stuff. So hopefully that was okay. Kind of lost my nerve there at the end, but it's actually worked out all right.